Hi, this is Matt Pellin going over the work I've done in OPL this semester. So the first exercise was just to do something interesting with the lambda calculus. And as you can see, I started by just going through all of the examples that we did in class and writing them down in Python. I chose to do Python just because I'm familiar with the language. And so as you can see, I did the booleans, integers, etc. just to get a hang of how writing the lambda calculus in Python was going to work. And then once I got the basic operations working, and after I had figured out recursion, so actually the first thing I did was write factorial function. And writing this actually ended up taking me a lot longer than it should have because Python does not short circuit lambda calculus booleans. And it took me a while to figure out that that was actually the problem because I kept getting infinite recursion. And the issue is that when you have, this is what it would normally look like, the makeFact function, but in Python, it will pass 1 to the resultive is 0 of x, and then it will evaluate x times x minus 1 factorial before passing it to is 0. So when normally if you do the beta rule, you will notice that it would get rid of this and short circuit and just return the 1. Python will evaluate this, resulting in infinite recursion always. So it took me a while to figure out a workaround for that to make this work with Python. And the solution that I came up with, as you can see here, was instead of having the arguments to the Boolean be just 1 and x times x minus 1 factorial, I chose to have a lambda that returns 1 and a lambda that returns y times y minus 1 factorial. So I passed those lambdas to the Boolean, which means that Python won't evaluate the body of the lambda yet because they don't have arguments. Then is 0 will return which lambda, and then I call that lambda with x. So this basically just forces Python to short circuit by not allowing it to calculate the contents of the function until the Boolean has determined which one should be called. So that was the hardest part of figuring out the recursion, because just doing the recursion itself took me a little while to just figure out exactly how it needs to be structured in Python. But this figuring out that you needed to pass it a lambda instead of the actual function you wanted called took me a while to figure out that that was what it needed, and then it took me even longer to figure out how to fix it. So then once I did that, I also managed to create a division function which uses the recursion to basically make a for loop. If you're trying to do x divided by y, it increments z starting from 0 until z times y is greater than x, and then returns z minus 1. So it does integer division with truncation. So I was pretty proud that I was able to get the recursion working for division, which also obviously required me to write some logic functions for comparing lambda calculus numbers, which was something that I was having trouble conceptualizing when we were going over them in class, how you would do that. But then once we had the subtraction, it started to make more sense. So doing those really helped me understand that. And then I wanted to make a binary search as my something interesting, which obviously means first I had to create an array structure. So my array structure is like this, where the array is a pair of size minus 1 or the index of the last element paired with the actual array, which is a pair of the first n minus 1 element subarray and the last element. So if in Python your array would be 0, 1, 2, 3, like that, my array would look like this, where each of the parentheses indicates a pair object or pair function. You'll notice that there's an extra 0 here. That's just because every element in the array needs to be a second element of a pair in order for my functions to work and be consistent the way that I structured them. So this 0 isn't actually part of the array, and it isn't accessible by the array functions. It solely exists so that the first element of the array can be the second element of a pair. So as a total, my array structure would look like this for the given array. The first element is 3, which is the index of the last element, and then the actual structure looks like this. So once I had that figured out, the next step was to write all the array functions. So appending was the easiest because that was what I based this structure off of. I wanted to be able to like append easily. So for append, you would just create a pair of this value incremented, which is that line right there, paired with the array passed false. Oh, that's the wrong function. This one. increment array of true paired with array of false. So array of false gives you this whole array paired with x, which is the new argument. So you create a pair of this with the new next argument, and you increment this value to get the new array with the extra appended value. Indexing an array, yeah, this is easiest to explain through an example. So if you want the second index, what you do is you take this value here, the index of the last element, and you subtract the index you want. So if you want the second element, you would do 3 minus 2 is 1. So that's this right here. And then that many times you're going to call this r_iter function, which passes true to the array. So you start with the base array, and then you pass true that many number of times that you want. So if you want the second index, you would pass true once, which gives you this array. And then once you're down to the correct level, then you just pass false to get the actual value at that level, which would give you the 2. Subarrays are similar, except they would, from iterating from I to j, they use j like the index and the last index function, except they stop here before passing false to get to the 2, so they would stop and have that whole subarray. And then what it does to get a subarray from I to j is it sets this value to j minus I. So that doesn't actually remove elements before I in the array, but what it does do is it tells the array that there are no elements down there. So even though this 0 does still exist, as far as the array is aware, it only has the 1 and the 2. So that's how the subarrays work with this array object. And once I had the array object, then I tried to make the binary search because I now had all of the functions I need, but I was not able to actually get the binary search working. So I just based it off of like a normal binary search where you check if the center value is the value you want. If it is, you return the index. Otherwise, check each of the subarrays. But for somewhere in here, my logic is incorrect, and I either get infinite recursion or I just get a wrong value. And the Python debugger isn't really built for really well debugging functions like this that just have all of these nested functions and lambdas. So it wasn't really helpful to try and determine what was going wrong. So I wasn't able to, in Python, create the binary search because I just couldn't figure out what was wrong with my implementation. But I was able to create the array, which I was pretty proud of. It took me a couple days to try and figure out how I would structure an array such that I could create all of these append and indexing functions easily. But I did end up figuring out how to do that, so that was definitely the hardest part of trying to get that working. So then, as just an example of some of it working, I created these transition functions just to make it easier to see what's going on, just converting between lambda calculus, integers, booleans, and arrays to Python booleans, integers, and arrays. So just as an example of it running, you can see I started with just a normal Python array, and then I just converted to a lambda calculus array. And then I use the functions I created to append 7 and 9 to it, and then I print it out. And you can see here it's correctly has the 7 and 9 appended. And then I try to do the subarray from 2 to 4, which correctly prints out just the elements 2, 7, and 9. And then if you want the third index, it correctly prints out just 7. And then as an example of the factorial working, I just called the factorial on that third element, and it correctly outputs 5040, which is 7 factorial. So doing all of these functions really helped me to understand mostly how the lambda calculus can be used to create things that you wouldn't normally think can be created by a function, like doing division with only functions or creating an array only using functions. It really helped me to understand the power of the lambda calculus to create data structures, really, which I thought was really cool, which is why I wanted to go further and try and make the binary search, even though it didn't end up working. So then for exercise 2, we had to create an ISWIM interpreter. So I started with just creating an expression class because it helped me to conceptualize that everything is an expression, and then I had a subclass of expression, which is values, which are abstractions, constants, and variables. So then for each of these, I just gave them the member variables that they should have based on what kind of structure they are. So like an abstraction has a variable and an expression. In my case, constants are just integers and variables are characters or strings. Applications have a function and an argument. Operations have the op, the values that have already been simplified, and expressions that have not been simplified. And then I wrote the simplify functions, where for operations, the simplify function checks if there are any expressions left to solve. If there are not, it calls the delta function on itself, which just evaluates an operation. And if there are expressions left to solve, then it grabs the next expression, does one level of simplification on it, checks if it's a value. If it is, it moves it to the values array. Otherwise, it puts it back in the expressions because there's more work to be done. If you tell an application to simplify, it will, in accordance to the order based on the standard reduction, it will first try to simplify its own function. If its function is already a value, then it will try to simplify its own argument. If its argument is already a value, then it will call the beta function on its function component, passing its argument component to that beta function. So what that does is the abstraction has the beta function which calls substitute on its expression with its own variable and the new value to replace that variable with. And so that's where these substitute functions come in, where if you try to substitute into an abstraction, it first checks if the variable being substituted is the same as its own variable, in which case it stops to maintain its own scope. Otherwise, it calls substitution on its expression. And then if you get to a variable while you're substituting, it checks if the variables match. If they do, it returns the new value. Otherwise, it just returns itself. And then an application calls substitute on its two components, and operations calls substitute on all its components. So this was probably the easiest of the three exercises, just because it consisted just simply of creating these classes and implementing those simplify functions based on what we defined as the standard reduction in class. So it was basically just transcribing what we did in class into Python, which ended up being fairly simple. I didn't run into really any major issues or bugs with this. So like I did several tests to make sure that it could maintain scope, making sure that it correctly simplified expressions in the right order. And then as my final test, I created this large expression, which included basically everything I could think of to throw at it. And it does in fact correctly simplify it. You can see it shows every step of the simplification, so I can ensure it was doing it in the right order. And then I also checked it with an outside source to make sure that the answer was in fact 18. And so this does in fact work, and it's easy to see what steps it's taking. And so as a whole, doing this exercise helped me to, the main thing it helped me to understand is why this is so inefficient, because it's easy for me to see, looking at all these classes, how every time I call this simplify function, it goes all the way down into the most base element of the expression, does one step of simplification on it, and then scales all the way back up every time, doing a lot of unnecessary work and unnecessary function calls. And the other thing that the doing exercise 2 helped me with was it really helped me with getting a start on exercise 3, in which I created a CEK machine. So I started by just copying over all the classes from exercise 2 with, I got rid of the substitute and simplify functions because we didn't need those anymore, and a few extra changes are that abstractions are no longer values because we have closures now, which are values and have abstractions and sigmas. The sigmas in my case are just a Python dictionary, which is just an associative array basically of the variable's name and the value it's going to be replaced with. And then I also created the K classes, which is the FN and R, and as discussed in class. And I also created this op, which I'm going to get to in a minute. So then my CEK, I designed it as a recursive function. And just like exercise 2, the easiest part was just transcribing the rules as discussed in class, which are these rule 1 through rule 6, which are just exactly as we discussed in class. I check what they are instances of, and if they match the left side of the rule as we discussed in class, then I call CEK on the right side of the rule as discussed in class. The problems I started encountering were that there were some cases that our CEK doesn't cover. For example, the CEK rules, as we talked about in class, can't handle a constant being passed to the CEK, like just a constant. If you call the CEK with 6, it doesn't know how to handle it, because the only times that it can accept a value are when k is an argument or k is an fn right here. But this rule is specifically only for closures, really. But then, so I had to figure out where and how I needed to create this new rule for just constants. And so I needed to make it specifically when k is not an R. I didn't have to specify when it wasn't an fn, because, excuse me, the only time k is fn and you have a value is you're looking at a closure. So by adding in this new rule here, I allowed it to take care of situations where it's just given a constant, or where you have a lambda like lambda x returns 6, and then it just call it with 8. That also similarly couldn't be handled because you end up with a constant being passed to the CEK machine with a k of end. So I had to add this new rule just to allow for those specific situations. And for example, I have that test right here, that exact function I just said. And as you can see, my CEK machine correctly does return 6 when that function is called, because of this new case. And then the other new rules that I needed to add were for operations, because we just didn't discuss those at all in class. So I added basically 2 new rules. The first one is if there are expressions left to solve in the operation, then it grabs the next expression, removes it from the expressions list, and adds to vals the result of calling CEK on that expression. And this is where I had to create this op class, and this was the hardest bug for me to solve with the CEK, because originally I wasn't sure what exactly needed to be passed for k as going into an operation, so I tried just passing k, and I didn't realize what was going wrong with it. And what was happening was that it would go in, and one of my functions right here has a lambda, so it would go into that lambda, but then when it popped out of that lambda, it would exit one layer further, and it would exit the operation and go further outside, so it would never finish evaluating the operation, which ended up resulting in it doing this whole operation first and then this operation, which was giving completely wrong outputs. So that's when I realized that I just needed to wrap the k in some other class. It's because this is the issue right here when it calls k.k. So I just needed to wrap it in an op class, such that when we call k.k, it returns to the original operations k, which results in us going back into this case properly and finishing the operation. Because once all the expressions have been evaluated, you just get to this case, and it calls delta on the expression, and then it calls CEK on that, the result of that delta, with the same sigma and the same k. So once I figured out that we needed to add this op, then it worked perfectly. And as you can see, passing the same exact result, the same exact expression as I showed in exercise 2, we correctly get 18. So this was definitely the hardest, just because trying to create these rules and make sure that they maintain the correct scope and the correct k was really hard to conceptualize and make sure I got it right. But getting it actually working and finished was very satisfying. And doing this helped me to understand the creation of these rules and what the logic behind how they work, because before, like, when I just copied these over, I was kind of just blindly copying the rules from the notes without really understanding them. But having to create some more rules myself really helped me understand where these rules come from and why they are structured exactly as they are. So that's really, one more example is that this is the example we showed in class of why what a bad CEK would do, and it would incorrectly replace this x with 6. But as you can see, mine does properly maintain the scope and does error out there. So doing this just really helped me understand the basis behind all those rules and understanding where they come from. So that was really cool. And that's all that I've done so far in OPL. Thank you.